You know that feeling when you have to pick the best option out of a whole bunch of them? The best ad campaign, the best teaching method, maybe even the best recipe for cookies. So you get some data, you look at the averages, and one seems like the winner. But here's the million-dollar question. Is it really better, or did it just get lucky? Nailing this down is crucial, and thankfully, we have an amazing statistical tool that helps us find the truth.
So let's make this real. Imagine you're a manager, and you've got 3 new, promising training programs. You run a small test, you get the scores back, and now you've got to decide which one to roll out to the entire company. That's a big decision. A lot is riding on it, so you need to be absolutely sure you're making the right call.
Okay, so here's our data, and at first glance, it looks pretty simple, right? Program C has the highest average. Case closed? Well, not so fast. Look a little closer. Someone in Program A got an 85, which is the same as someone in Program B. And check this out. The top score in Program B, a 91, is actually the lowest score in Program C. The data overlaps. It's kind of messy. So, is that higher average for Program C a real, meaningful difference, or is it just random statistical noise? This is exactly the kind of problem where we need to bring in a statistical heavy hitter, a tool that's designed precisely for this kind of messy, real-world comparison, and it's called analysis of variance, or for short, ANOVA.
ANOVA was developed by the absolute legend of statistics, R.A. Fisher. It's the go-to method whenever you need to compare the averages of 3 or more groups all at the same time. It's what lets us go from kind of squinting at the numbers and saying, I think this one looks better, to being able to state with real statistical confidence, yep, this one is the clear winner.
So how in the world does it work? Well, the real genius of ANOVA is that it all boils down to a very simple but incredibly powerful idea. It basically thinks in terms of a signal and noise.
Okay, so first up is the signal. The signal is the thing you actually care about. It's the difference between the groups. For our example, it's the variation between the average scores of Program A, Program B, and Program C. The bigger the difference between those averages, the stronger the signal.
And you can literally see that signal right here. The bigger the gaps are between these bars, the louder our signal is, and the more likely it is that we have a real effect on our hands.
But, every dataset has noise. Noise is just the natural, random variation that you find within each one of those groups. Think of it like background chatter that can sometimes make it hard to hear the actual signal.
I mean, even if you give people the exact same training, some will just naturally score a little bit higher or lower than others. That's just how it is. This natural spread of scores inside each program, that's the noise. And our signal has to be strong enough to rise above it.
And that brings us to the core question that ANOVA answers. It is, quite simply, is the signal strong enough to be heard over the noise? It does this by mathematically comparing the variation between the groups, that's our signal, to the variation that exists within the groups, that's our noise. It's all about figuring out if the differences between our programs are big enough to actually stand out from all that random individual performance chatter.
And the best part? ANOVA doesn't just give you a vague maybe. It takes this whole complex comparison of signal to noise and boils it all down into one single, clear, decisive number.
That when you run the analysis, you get a table that, I'll admit, looks pretty intimidating. There's a lot going on here. But this table is doing all the heavy lifting for us. And the good news is, you don't have to get lost in the weeds, because all of this math leads to one final number. And here it is. This number is called the F ratio, or sometimes the F statistic. And this is our verdict. It's literally the ratio of the signal to the noise. And for our training program data, the F ratio comes out to 3.88.
So what does 3.88 actually mean? Well, the interpretation is wonderfully simple. The bigger the F ratio, the stronger your signal is compared to the noise. If you get a small F ratio, something close to 1, it means your signal is basically just as loud as the random noise, so probably nothing there. But a number that's significantly larger than 1, like our 3.88, is telling you that the signal is punching through loud and clear. The differences you're seeing are very likely real. So now that we have this core logic of signal versus noise, you can start to see how flexible it is. We can actually apply it in more complex situations too. So let's just quickly touch on the 2 most common types: one-way and two-way ANOVA. One-way ANOVA is pretty much what we've been doing. We're looking at just one single factor. In our case, it was the training program. Simple enough. But what if you wanted to test 2 factors at the same time? For example, what if you wanted to know not just which machine is most productive, but also which operator is the best? And maybe if there's a specific operator-machine combo that's like a total superstar, that's where two-way ANOVA comes in.
It's incredibly powerful.
And you can really see the difference right here. On the left, you've got a classic one-way problem, comparing different fertilizers. On the right, a more complex two-way problem, looking at operators and machines. The underlying logic is exactly the same. It's still about finding that signal in the noise, but you can see how it scales up to answer much more interesting questions.
Okay, so let's wrap this up. What are the key things to remember? First, ANOVA is your go-to tool for comparing the averages of 3 or more groups. Second, its real power comes from that super-intuitive signal-to-noise comparison. Third, that F-ratio is your final answer. A big number means you've likely found a real difference. And finally, it's just an incredibly powerful way to find meaningful patterns in what can often be a very noisy world.
So the next time you're faced with a bunch of different options and some messy-looking data, remember ANOVA. It gives you a systematic way to listen carefully for that all-important signal and to tune out all that distracting noise. Which I think leaves us with one final question to think about. What hidden signals might be waiting in your data?